Hi and welcome to another lesson in the memory series. This time we are going to talk about memory structures. Objectives of this lesson. We will study structures, maybe unexpectedly. We will learn how to organize our data and our programs using structures. Finally, we will understand the idea of unions and how to use them. Giving meaning to your data. The processor cares about bytes. However, you care about the meaning of your data. This is some kind of a conflict. On one side, you want to make sure that the processor understands your program, and on the other side, you want to make sure that the program is meaningful to you and to your fellow programmers. Let's look at an example. How to store a point in memory. Let's begin with something basic. A two-dimensional point has two coordinates, just like in this picture. For example, this point 4, 3 is represented by two coordinates, the x coordinate and the y coordinate. For example, we could use two consecutive d words to represent a point. This is how it is going to look like in memory. This is the x coordinate, those 4 bytes, and this is the y coordinate. At this point you should know that because of endianity issues, the numbers are written from the left to the right and not the other way around. That's why the 4 is on the first cell and not on the fourth cell. I just want to emphasize that this is how the processor sees things, and this is about how you think about things. And it is very important that you can do both of those things. You can both think about your data in a meaningful way and understand its deeper meaning. For example, here the deeper meaning is that we are thinking about a two-dimensional point. And at the same time, you should be able to think about your data the way that the processor can understand it. And in this example, it is just an array of bytes in memory. Points declaration. Let's begin with declaring one point. This time we are going to use actual code to declare a point. So we just put some placeholders in the BSS section for two D words. We call the label PNT, which stands for point, and we put the first D word here and the second one here, and this is a total of 2 D words. How can we use this data? If we want, for example, to initialize the coordinates of the point, we can just access the first D word and the second D word in the usual way. We just move to address point, the D word 4, and then we move the D word 3 into address point plus 4. So we stored exactly 2 D words. It looks like we've solved the problem. We managed to create a point in memory. However, there is a problem here. This code is a bit hard to understand. Imagine, for example, that someone just reads this part. Maybe it is somewhere in the middle of the code, buried somewhere. And your fellow programmer looks at this code. He has to guess. He has to guess that this part of memory is probably the x coordinate, and this one is probably the y coordinate. And it is not that easy to guess this idea. Imagine, for example, a more complex structure. For a more complex structure, it will be pretty hard to guess. Maybe we should find some kind of another way to do it. Let's try something else. This time we declare a point, but we use two labels. I want to emphasize the difference from the previous example, so let's take a look again at the previous example. In this example we have only one label, and in the new example we have two labels, px and py. Both point to D words. This is the first D word and this is the second D word. In the code section, or the text section, we do the same thing, but this time it looks a bit different. we move the dword 4 into the address px and the dword 3 into the address py. Basically, this piece of code and the previous piece of code are going to translate to exactly the same encoding in the executable file. Basically, if you write those two pieces of code and then assemble each of those examples, you are going to get exactly the same executable. The only difference is about the readability of the code. When your fellow programmer is going to read this code, or maybe you are going to come back to your code only after a few months, and then you look at this piece of code here, it will be a bit easier to understand that this is probably the x coordinate and this is the y coordinate. As opposed to the previous example here, where we don't really know what the fields are, the fields in this compound structure. But here it is a bit easier to understand. But only a bit. Maybe we can do something even better. I want to take a look at another example, this time about declaring a line, which is basically just 2 points. If we think about it, every line could be defined by 2 points. Maybe the first one is the first point and this is the second point, and we get a line using 4 numbers, 4 dwords. How can we do it with our code? We declare a first point, which we are going to call p1x and p1y, and both of these are going to be dwords. And this is the second point, declared mostly the same, but we just used a bit of a different label to make sure that we don't have the same labels. Now if we want to initialize the line, we have to do the following. We put 4 into the address of p1x, 3 into p1y, and so on. For the other point, we put 5 and 1 into p2x and p2y. Now, this is beginning to be not so fun, because just to declare one line, we have to put all those lines, and look at the comments. We have to put comments because whenever someone is going to read this code, he might not guess that this is a line. So we have to say, this is a line. We are declaring a line here. And we have to say, this is the first point. This is the second point. This is less cool. We don't want to get into this kind of situations. What are actually the problems with the line example? We have it here in a very small snippet of code. I only took part of it. First, we have to write 4 lines of code just to declare one line structure. Every line in our program is going to take at least 4 lines of code just to declare it. Another thing, it is hard for the reader to understand the bigger line concept. There is a bigger concept here. I know that we just have 4 dwords, but the bigger concept here is that we are talking about a line. It's a geometric creature, and if the reader of the code looks at this kind of code, it just sees 2 points, or maybe it just sees 4 dwords. And this is a bit sad, because you can't understand big things if the only thing you can see is 4 dwords. There is not much meaning to it. Another thing, we might later want to create something more complex. For example, maybe we want to create a triangle. And at that point, we might want to reuse the point concept. But then we have to write the same lines of code over and over again. For example, if we use 3 points to declare a triangle, we are going to have 6 lines just for one declaration of a triangle. It's not going to be fun. And then the final question, what if we wanted to change our point to be 3-dimensional? Maybe in the project that you and your coworkers do, you finally realize that you have to use 3 dimensions instead of 2. Then you will have to change every line definition in your code, which means that it won't be enough just to make a small change. You will have to change every line definition or every line declaration in your code. And this is going to be pretty hard and error prone. So there is a solution. The assembler can help us define our data structures. The struct assembly directive allows to define data structures, and it looks like this, basically. We first have to put the definition, which looks like this. It begins with this directive struct and ends with the ends directive, and this is the name of the structure that we define here. Basically, this is only a definition, the part that I'm showing here. By itself, it doesn't do anything. It is just an idea and it helps you write your code. We can see inside this structure two fields. The first one is called X, and it is of size dword. The second one is called Y, and it also of size dword. Now that we have this structure definition, we can declare a point in our BSS section, or maybe in our data section if we wanted to. And we declare it like this. My point, this is the name of the memory that I want to declare. This is the label, my point. And PNT is the name of the struct. This is PNT. And finally, I put a question mark because I don't want it to be initialized. Remember, I put it inside the BSS section. This is why I did it on the first place. How can I use this kind of struct? Let's look at the code. Move dword myPoint.x4. This is something special. We didn't define ourselves that thing, myPoint.x. It was done automatically from this declaration. So myPoint.x actually refers to the first dword, and myPoint.y refers to the second dword. Basically, the resulting binary from this code is going to be the same, just like the previous examples that we had about points. This declaration is going to declare exactly two dwords, and this part of the code, this instruction, refers to the first dword, and this one refers to the second dword. I want to remind you that struct is just a directive. It is not an instruction, which means that your structs will not show up in the final binary. They just help you to write your code. In fact, the assembler does the dirty work for you. You write this kind of code, which is pretty readable. It looks much better to human beings than the previous examples that we have seen. And the assembler is going to understand this code as this code. The assembler is going to do this transformation from this kind of code, which is very readable, to this kind of code, which is more basic. If we didn't have the structure mechanisms, we would have to write this kind of code, which is pretty unfortunate. I just want to make sure that you understand. The struct mechanism is just a shortcut for writing code. You write this kind of code, and then you can write this kind of instructions in your code section, and the assembler is going to understand it just like this. Here we can see that the point is declared just as two row dwords. And here we just refer to the first dword and the second dword. This code and this code are exactly the same. Defining structures. Let's talk more formally about how to define structures. Every definition of a structure begins with the struct directive and it ends with the ends directive. I think it is pretty easy to remember. Begins with struct, ends with ends. Everything in the middle is considered to be data inside a structure. So here we have those X and Y, which are the data inside the structure. Structs are usually defined before any section definitions. In the previous example, we can see that the struct is defined outside any section. It is not included inside any section. Just to be more exact, you could define it anywhere in your source code, wherever you want, because the struct is not actual data, the struct definition. the definition is not really data or code. It is just an idea, and the assembler is going to read it at some point. You just have to make sure that you define it early enough so that whenever the assembler is going to spot, for example, the word PNT in the source code, it will be able to understand that it is a struct that you have defined before. The order somehow matters, but it doesn't really matter if you put this definition inside the section. It means nothing. The definition creates a set of labels, and basically this is what the struct definition actually does. This is most of what the struct definition does. It just creates a set of labels. For example, the point struct that is defined here is going to create this set of labels. pnt.x equals 0, pnt.y equals 4, and also a special label which is called size of .pnt equals 8. This last label is kind of a strange label. Maybe the label won't be even the right name for this kind of thing. Size of .pnt, you can think about it as some kind of a constant, which is the total size of the structure. Y8, here in this example we have x, which is of size 4 bytes, and y, which is of size 4 bytes. Together we get 8 bytes. So this is the size of PNT. Whenever you define a structure, you get this constant automatically, and you can use it anywhere in your code. It makes the code much more readable if you use size of .pnt than if you use 8. The reader of your code will not understand what is 8, but he will definitely understand size of .pnt. In addition, you may pick default values for the fields of the struct. For example, I could define PNT like this: xdd3, ydd5. And now, whenever I define PNT in my data section, it will be initialized with those values. And by the way, if you choose to pick default values, then it will only be meaningful if you declare your points in the data section and not in the BSS section. The BSS is for uninitialized structures or uninitialized data. Structures declarations. So given a structure definition, we can declare data. Let's look at a more specific example. We have already seen some examples of this. For example, let's take a look at this definition, which we have already seen. In this code example, we can see two different declarations of the point structure. The first one is inside the data section. Here we declare a point with initial values. We call it myPNT1, and this is the label which points to the data. PNT is the name of the structure that we have previously defined, and 3, 4 are the initial values. So 3 is going to be x, and 4 is going to be y. These two numbers will be the initial D words inside the point structure. Another declaration, myPNT2. This declaration is inside the BSS section, which is the uninitialized data section. This point is not going to have any initial values because we declared it as myPNT2, then PNT, which is the name of the structure we have previously defined, and question mark, which means that this structure is going to be uninitialized. What do we get from the declaration? First, we get this label. For example, here we get the myPNT1 label, and we also get here the myPNT2 label. But this is the usual thing. We could already get this label just by putting here, for example, myPNT1 and then a colon. This was the usual way to get a reference to some location, to get a label. But the declaration of a structure gives us some extra labels. It also gives us, for example, if we take a look at the myPNT example, it gives us the usual label, which is myPNT2, which is just the address of this memory. But it also gives us two extra labels, myPNT2.x and myPNT2.y. And these two labels are going to point to the X field and the Y field of myPNT2. Their values are going to be, for example, this is just an example for this kind of values. Maybe this large number, 402000, and then myPNT2.x is going to have the same value as myPNT2, because X is the first field. So it should have the same offset as this label, myPNT2. So it has the same value, the same label value. And finally, myPNT2.y is going to have this value, which is 4 bytes larger than myPNT2.x. That is because X is of size 4 bytes. So X is going to be in this location in memory, and Y is going to be in this location in memory. I said that this is just an example, and I meant that you could get a different number if your program is loaded to a different location in memory. This number depends on the location where your program is loaded. It depends on the location of the data section and the BSS section. Maybe if we switch places and put the BSS over the data section, we will have different numbers. Another thing that I want to emphasize. We have already talked about a few labels that we get. We talked about the labels that we get from the definition, and now we talked on the labels that we get from the declarations. And those are different labels. A good way to remember it is the following. The labels that you get from the definitions are small labels. They have small values. I return for a moment to the previous slide. We can see here the labels that we got from the definition. These are really small values. So the definition usually gives you small numbers for the labels. PNT.x is 0, PNT.y is 4, and the size of is also not a very long number. But the labels that you get from the declaration, they actually represent real data. Data that was already assigned a place in memory. So those are going to have large values. They are going to have actual addresses in memory. That's why myPoint2 and myPoint2.x and .y have those large numbers as values. This is a relocation in memory, as opposed to these numbers, which are just offsets from the beginning of the structure. They are not real addresses in memory. They are just offsets, but these are real addresses in memory. It is very important to remember the difference.